Hello everyone, this is lecture section 2.3, Math 232, Linear Algebra, Simon Fraser University. My name is Randall Pike. Today we're going to take a pause in our development of the theory and do some examples to illustrate how we use the process of row reduction and solving linear systems of equations to answer basic questions, fundamental questions in linear algebra. So the questions we'll address today in today's lecture, and you will do it from time to time throughout the course, will be discussions about the span of sets, their linearly independence, and determining whether sets of vectors form a basis. Okay, so let's work through a couple examples here. The first example is this question about whether a vector is in the span of a set of another set of vectors. For example, here's an example in R4. We have this vector u on the left here, and we wonder whether it's in the span of these three vectors. Okay, three vectors in R2. Okay, so what does it mean to be in the span? I.e., are there scalars, so one for each vector in that set? There's three vectors in that set. Let's call them v1, v2, v3. Okay. Are there scalars c1 and c2 and c3 so that we can write u as a linear combination of those three vectors? So here we are, c1, v1, c2, v2, plus c3, v3. Okay, so that's what it means for u to be in the span of the set. Since the span of the set is the set of all linear combinations, for a vector to be in the span of a set of vectors, it must be a linear combination of those vectors. So a linear combination of these three vectors would be a combination of this form. I need three scalars. Can I find three scalars so that this sum on the right adds up to u? All right, so that's using the definition of span of a set of vectors. Okay, so we needed to know what that means, the set of linear combinations. And then we had to proceed to answer this question by identifying that we need to determine whether a certain vector equation, which is this one, this is a vector equation, can be realized. So are there C's which make this true? Now we're going to reduce that, like we often do in this course, into a problem about a linear system of equations. So how do we obtain a linear system of equations from this basic vector equation, which came directly from the problem? So obtain a system of linear equations. Okay, so that's our task now. And this will be your task in many questions that you will encounter in this course, many abstract questions. They will be reduced to solving a system of linear equations. So let's see how it's done in this particular context. So this being a vector equation here, so equality of vectors, remember? And at the very beginning of the course, we defined what equality of vectors means. It means each component is the same. So I'm going to go through the components of u and compare each of its components to the components I see on the right. So let's do that. So here are the components. I'm going to list them from left to right. So the first component I see on the left is in u. I see -1. Now I look at the first component I see on the right-hand side, and it's a combination of those first components of the three vectors v1, v2, v3. So if I look at v1, and I'll highlight it a little bit up here, I see there's a 1 in the first component. And then this sum down here, the first term, you see that? It's c1 times v1. Now c1, scalar multiplication, remember, is realized algebraically by multiplying each component by that scalar. So I know that the first component of this vector c1, v1 will be c1 times the first component of v1. And the first component of v1 is 1, so it's simply c1. Okay, now I'm going to move over to the next first component, the first component in the second vector of that sum. Remember, the right-hand side, the vector on the right-hand side its first component will be the sum of the first components of the three vectors I see there. Okay, these three vectors. Remember, that's the algebraic realization of vector sum, is you add components. So I'm moving across this sum. I'm now in the second term, C2, V2, and I look at my vector V2 up there, and its first component is 0. Okay, so I'm not going to get a first component from the second vector C2, V2. So I'm going to leave a space there. I'm going to move on to the third term, C3, V3. I look at my V3 vector. I see a 1 in the first component. So the first component of that third vector, C3, V3, will be just C3. So I'm just going to put plus C3. Okay, so let me just summarize what we see here in this one equation. If U is supposed to be equal to this sum on the right, then the sum C1 plus C3 I see there must be equal to -1, because I need it to be equal to the first component of U. Okay, so that's one equation in the three unknowns. Let's move on, and we obtain another equation by going to the second component. Remember, vector equality means all components must be the same on either side of this equality here. So the second component of U now is 6. Okay, so that's the left-hand side. Now, what's the second component on the right-hand side? And I'll do the same thing. I'll look at the second component of V1. I see it's a 2 there. So the first term I see on the right will be 2 times C1, because the second component of the vector C1, V1 will be 2C1. All right, I'll move to V2, and I see a 5 there in the second component. So the second component of the vector C2, V2 will be 5 times C2. Okay, I move to the vector V3. I see a 0 in the second component. So that third vector, C3, V3, will not contribute to the second component. So that's the equation for the second components. I need that 2C1 plus 5C2 must equal 6. Okay, so continuing on to the third component of U, which is -5. And then I start at the left again. I look at the vector C1, V1. Its third component is 3 of V1. So the third component of C1, V1 will be 3C1. I go to the vector V2. Its third component is -3. So the third component of C2, V2 will be -3C2. I look at the vector C of V3. Its I'm on the third component is 7, right? Good. 7. So the third component I see on that equation on the right will be in C3, V3. Its third component will be 7C3 plus 7C3. Okay. And now I go to the fourth and last component. In U, I see -8. And I work my way across the right-hand side looking at the fourth component of those three vectors. So for the first vector, I see 4C1 in its fourth component. I see C2 in its fourth component, and I see -2C3 in its fourth component. So this is the set of the system of equations I need to solve. So you see how I obtained a system of linear equations from our problem as stated at the beginning about the membership of a vector in the span. I translated that using the definition of span into a vector equation. And from the vector equation, I found a system of linear equations in these unknowns, C1, C2, C3, by looking at the components of each vector on the left and the right. Okay, so the unknowns are the CIs. So what is our system? So now we go to our procedure of solving a system of equations by using an augmented matrix. So I'm going to write out the augmented matrix of this system. So here we go. So it's going to be, C1, yeah. So let's write out this augmented system. So I'm going to put, this is the right-hand side right here, okay? So that's the right-hand side. So that's going to appear on the rightmost column of my augmented matrix. Now my matrix, remember the C's are the unknowns, so I'm going to just put above each column what a variable, what unknown it represents, and this is my right-hand side, okay? So for the C1 column, I see in my first equation there's a 1, in the second equation there's a 2, in the third equation a 3, in the fourth equation a 4. Okay. And then in my first equation, I don't see a C2 there. In my second equation, there's a 5, third equation a 3, fourth equation a 1. And in C3, I see a 1 in my first equation. It's not in the second equation. There's a coefficient of 7 in the third and minus 2 in the fourth. And then my right-hand side, minus 1, 6, minus 5, minus 8. Okay, there it is. So there's my augmented system. Okay. Now we row reduce it, and since that's not the object of this lecture, I'll just tell you what it is. So this can be row reduced to this form. So I'll get leading ones in the first, second, and third columns. And the fourth row is entirely 0. So minus 2, 2, and 1. Okay, so that's how it's row reduced form. And I see that there's a unique solution. And it is C1 equals 2, C2 equals 2, C3 equals 1. And so what I know is that the vector u is given by this linear combination. And you can check that it is. Okay, so if you add up this linear combination of v1, v2, and v3, you will see that it does in fact equal this vector. Now, while we have these examples here, it's nice to tie in some more ideas, once you've done this work. So we note it's a unique solution to this problem because the set v1 to v3 is linearly independent. Okay, that's a consequence of linear independence, that these linear combinations of vectors are unique, and that's very important. That's why we use them as a basis. So let me finish the sentence. Unique solution because the set v1, v2, v3 is linearly independent. And we're going to talk about addressing that question in particular below. Okay, but just keep this in mind. It's linearly independent because if I row reduce just this part of the matrix, in other words, the coefficient part, which is the v1, v2, and v3, you can see v1, v2, v3 vertically there. So let me add that parenthetically here, because the rank of this matrix with v1 as the first column, v2 as the second column, and v3 as the third column is 3, the same number of columns. So that will be mentioned again below. Okay, but we've done the work, we've done the row reduction. We can also extract that conclusion about this situation, that the set of vectors is linearly independent. And as I mentioned, a consequence of linear independence is whenever a vector is a linear combination of those vectors, that linear combination is unique. There's only one way to do it. Okay, so that's problem 1. Problem 2, okay, so I've slightly reworded this statement, make it a little bit more clear. It was accurate previously, but it's just a little bit more clear. So I'll reread it, my slightly modified version. We start with a subspace. Now, you should think about this. A subspace, the easiest way to define a subspace is simply by specifying a span of vectors, like up here. So here's a subspace W, and you know it's a subspace, right? Because we've already established that the span of any set of vectors is automatically a subspace. It's closed under those two conditions. So this W here, this is a typical way to define a subspace by listing a set of vectors as its span, okay? Now these vectors, in this case, they are linearly independent, but they don't have to be. It's just any vectors. You take the span of any set of vectors, the result is automatically a subspace. So typically, that's the way we identify subspaces, but not always. Okay, so you might think in this sentence here, take a subspace defined as a, if someone gives you a subspace, typically it will be defined as a span. Okay, and now we want to express this subspace in a different way. We want to define it differently. That's what this question is about. And as we'll see in this example, I will do. every subspace can be realized as the solution set of a homogeneous system of equations. Okay, and I'll do this example right here. So for example, this W. Now here's a span of 4 vectors in R6. Okay, so that's a subspace. We will be able to determine a linear system of equations such that this W is exactly its solution space. Okay, and now that's another way to define a subspace, and it's a useful way too. So let's see how we do that, how we approach this problem. So I've given 4 vectors in R6. So the question of identifying the subspace is this one I've reworded here, is when is a vector in the subspace? Sorry, I don't mean that. How about this one? Yeah. When is a vector, an arbitrary vector in R4? Sorry, that should be, yeah, that should be R6. So let me just stretch that out a little bit. Okay. Okay. Right. X6 in W. Okay. So this question of identifying W is exactly, or at the beginning, you know, what is W? Okay, is exactly this same question. When is a vector in W? Okay, so how can I recognize when a vector is in W? All right, so that's the question. That's how we start this problem of identifying a system of homogeneous equations with this question here, which is very similar to what we just finished. Okay, because I asked that question up here. I said, when is this U in the span? Now that's a specific U. Okay, now down here the difference is I'm not specifying a vector yet. I just want to know under what conditions on these 6 numbers will guarantee that this X is in W. Okay, so that's another way of describing this W. Okay, but it's the same. I'm going to do the same procedures I did above. All right, now let's just review what that augmented matrix looked like so I don't have to do this work again. These steps right here, from vector equation to system of equations and then to augmented matrix. See these 3 steps? 1, 2, 3. That's what you should be concentrating on as you go through these problems. Don't skip down to step 3 and say, oh, I formed this matrix for this problem. Okay, although this matrix, if you recognize it, it is the columns are the vectors V's and the right hand side is the vector U you're interested in. That's not always going to be the case in problems. You're not always going to be putting the V's into columns and the unknown vector as the right hand side. So be careful and understand how we obtain this augmented matrix, this last one, from the question above through these 2 steps: vector equation, components, and finally into a system of equations. Now this is the same question up there, so I know what my augmented matrix is going to look like. All right, so I'm going to just draw it now because I know what the steps are. So my columns, okay, we can see them all. So my columns of this matrix will be first the column vectors that I see in that set of vectors whose span defines W. So I'm going to write them down. So it's 1, 3, 2, minus 2, 0, 2, 0. And then the second vector I see is this one. And the third vector. Okay, and the fourth vector. Okay, that looks right. Okay, now I'm not done yet, so I won't put that there. Then I put the right-hand side. Now here's the difference. The right-hand side are unknowns. So in this problem, the unknowns now are the components of this vector x. Because my goal is to give me conditions on these xi's that tell me it's in the set. So you see that? So it's the table's been turned a bit. Here the unknowns are the xi's, and although the columns represent the ci's still, right? So still C1. Maybe I'll put that in a different color. Here we go. You know, because I am looking at that same system of equations where I have these 4 c's adding up to x. In this problem, the xi's are the unknowns, okay? And the question is different. The question is, and I'll put it down here now, when is this system consistent? See, that's the question now. It's the consistency problem. System consistent. That is, when does it have a solution? Okay, now I should highlight that in a very obvious color. When is this system consistent? All right. In other words, when does it have a solution? Now notice I'm not interested in the solution. I don't want to know, I don't need to know what the C's are. I just need to know that there are such C's which can produce the linear combination to equal this X. So it's really about these X's. X's are the unknowns. Okay, Xi's are the unknowns. Okay. All right, so that's the question for this problem. When is it consistent? And that's an important step for you conceptually. It starts with this question here, Q, this Q question. When is X in W? It means that X can be written as a linear combination, which means this particular system of linear equations has a solution. Okay, so that's exactly what we did here, except here we found the solution because I had a particular U. I wanted to know what combination it is. Here I'm not interested. In fact, I can't tell what is the particular linear combination. I just want to know whether there is one or not. Okay, if there is one, and I should finish, if so, then X is in W. And why? Because it's a linear combination. Because X is a linear combination of those V's, of the VI vectors. Okay, if I can find a solution, it means there are C's which produce that linear combination which equals X. Good. So then that identifies the X in it. Now here we go. I'm going to do the row reduction. I'll just do I'll do a few steps here. So the difference doing this row reduction and previously is that the right hand side not being numbers, I have to keep track of them. So let me start off the row reduction, because I need to reach a point where I can tell whether the system of equations is consistent or not. Okay, and you remember how you identify inconsistency in systems of equations. It's when at any point in the row reduction you obtain a zero row in the coefficient part and a non-zero entry in the right-hand side part. Okay, whenever you see that at any point during your row reduction, you can immediately say that there's no solution to this system. It's inconsistent because that one equation that you've created there does not have a solution, right? When all the coefficients are zero, but the right-hand side's not zero, there's no chance of choosing your variables to make that equation true, all right? So that's what we're looking for in this problem. We'll see that for us, though, we'll need, because we want to know what are the conditions on the x's, we'll need to identify all such rows like that if they occur, not just find one and stop, but we need to find all of them, and you'll see why we need to find all of them. So let's proceed with this problem. So we row reduce. So I'll start at the top left. I see a nice leading one there. Okay. Now here's what we do. We do the same row reduction, except that the right-hand sides now are not going to be numbers, but they'll be, the x's will start to be appearing in all the equations as we do the row operations. So for example, in the second row, I'm going to create a zero here. Actually, I'll just put down all my zeros because that's what the row reduction is aimed for. 1, 2, 3, 4, 5, 6. So I'm aiming for this first column, right? That's our goal. Make this top one a leading one. So I'll start at the second row. So I put a 0 there because I subtracted 3 times the first row. So let's go across and do all the entries that way. And it turns out to be all zeros, okay? But the right-hand side is x2 minus 3x1. All right, so I'll emphasize right here, maybe a little different color. I like this, maybe not a blue, right? Because that's blue on blue. This is an interesting row for us. All right, so I'll just put a little red dot there. Okay, so that row right there already tells me that it does not tell me that the system's inconsistent. Okay, here's the key point. It tells me that x2 minus 3x1 must be 0. Okay, so I'll just make a little note here as we go along, and we'll piece it all together at the bottom. So at this point right here, I realize that, oh, I can't just choose my xi's arbitrarily. I have to choose them so that this particular combination of their coordinates is equal to 0. All right, so I see that right now. So now you might realize why we need to proceed through this row reduction until the end to identify all such 0 rows, because I need to know what there may be other conditions on the xi's that I need to satisfy for this x to be in W. And also at this stage right here, I can conclude that the span, I don't have to put it in such an alarming color, but the span of V1, V2, V3, V4, okay, V2, V3, and this will come up also later in an example, so it doesn't hurt to say right now. I know that the span is not equal to R6, okay, just because of that one sentence. Okay, remember R6, the VI's, and that's a 2, the VI's are in R6, but their span is not of all of R6 because this condition right here, I need x2 minus 3x1 on those vectors to be 0. Okay, so not any vector in R6 will satisfy that. Okay, so I can conclude at this stage, if this was the question, is the span R6? Here I could conclude that it's not and be done. Okay, but that's not our question. We want to continue further. I actually want to know, well, okay, the span is not R6, but what is the span? I want to be able to describe it to someone, to use it, to find vectors in it. Okay, so let's continue on. So let's put on the top one still. So now I'm going to the -2 you see up here, okay? The -2 in the third row. So I've added, to make that a 0, I've added 2 times the first row. Okay, so let's go down and add, sorry, 2 times the first row. So if I add 2 times the first row to that -5, I'll get a 1. If I add, and the next term will be a 5 because it's a 0. Now if I add 2 times the top row to there, and that entry, I'll get a 4. Sorry. I see a -4 in my notes. Is that... sorry, let me just do this again. So I'm going to add 2. Sorry. Sorry. Yeah. -1. Sorry. Yeah, I'm just getting my finger on my wrong page. Good. So I'm still good, right? I'm doing the algebra properly, so I'm working across row 3. Then when I get to the last entry, notice it's x3 minus 2x1. Okay. Now, this row, okay, this is not a condition on x3 and x1, okay, because I don't need it to be 0. So this is not of use for us. Then I go to the third row, I don't have to change because there's a 0 there. All right. So it stays like that. The fourth row, I subtracted 2 times the top row from it. Okay, so that gave me a 0 here. I have a 0 here. I have a 0 here. Okay, so this is another situation where I've created a 0 part in the coefficient column. So this was the 1, 2, 3, fourth row, right? So it's x5 minus 2x1, right? Because from the fifth row, going back up to the original one, from the fifth row, I subtracted 2 times the first row. So the right-hand side is going to be what I see on the right-hand side of the fifth row minus what I see on the minus 2 times what I see on the right-hand side of the first row, which is x1. Okay. So I'll put a little red dot there because that's another condition. You see, and that's a different condition. So I need also that x5 minus 2x1 being 0. So that's another condition on these entries. And then what do I have at the bottom row? It stays what it is. And am I putting, sorry, a 4? I'm just checking my numbers. They look like they're a little bit different here. Right, yeah. So I did miss a minus sign. So I'm just writing my notes as I go along. So there's actually a minus sign here. Good. All right. So that's just to be consistent with what I started with. So that's why there's a -3 here, and then 15, and an 18, and an x6. Okay, so you see how I've done that. But I'm not done yet. I need to get to the point where I've identified all the 0 rows, which is the reduced form, sorry, the row echelon form. It doesn't have to be reduced, but just the row echelon form. At this stage here, okay, I do another row operation. So let me give me more space here. Okay, so let's go again. So 1, okay, and then I'll do that. Okay, so I'll do that row operation also. So I'm going to write down, let me see, 1. So you see I'm starting to put my rows here. So I added a -1 there. So this is going to be 2x1. Sorry, let me get that right. 1 minus 5, 4, right? So 2x1. So I just multiplied it by -1. Okay. Okay. And then at the top, I'll leave it like that. So the top, I did the row reduction to get rid of this 2 up here, which I don't need to do, but I'll do it anyways. I really just want to concentrate on my 0 coefficient parts, the rows that indicate inconsistency. So where am I now? So now I have this bottom row with which will be this one here after the row reduction. Okay, then I'm going to put down my 0 rows. So this one I've seen already. This one is going to be coming from, now it's this row right here, the x4 one, right? So to get rid of this -2 there in that second column, I'm going to add 2 times my new row 3 to it. Okay, or subtract, yeah, add 2 times the new row 3. So it's going to be x4 minus 2x3 minus 4x1. All right, and then I have my other 0 rows, x3 minus 2x1, and then the other one. Okay, so I put them at the bottom, x5 minus 2x1. All right, so I did a few more row operations just to identify my 0 rows. Okay, so here, now this is of the form, this matrix, that I'm not going to create any more 0 rows. Okay, I don't need to go further on. For our purposes here, I just need to see these conditions. These are the only conditions that the xi satisfies. So conditions on xi, on the xi. All right. To assure that x is in W in the span of those vectors. Okay. Those are the conditions. So now it's another way to define this W. Okay. Another way to define W. Okay. And we can proceed a bit further with this to find W. Okay. So let's continue on. So remember the question was at the beginning, find a linear system, a homogeneous linear system. Well, we're almost there. So let's look at all our conditions. So remember, you can see that some of these xi's appear in more than one equation. So it's a simultaneous system of equations. We're looking at, we need solutions that satisfy all 3 simultaneously. So it's a system of equations. They don't exist independently. Whatever the xi's are, they must satisfy all 3 of these equations. Okay, and I'll just make a note here in blue because it's not that alarming. Note x6 does not appear in these 3 equations. Appear in these equations. And what does that mean? Well, it means that there's no condition on it. So no condition, and we'll give it a parameter. No condition on this one component. So x6 can be anything at all, okay? Because I don't see it appearing here, okay? But the other ones do, and that's 4. That's an x1, by the way, okay? But the other 5 do. I believe, right? Or x2 minus 3x1. Sorry. Am I, hold on, x2. Let me just check my notes here. I have x4 minus 2x3 minus 4x1, okay? Then I have sorry, I'm just making sure I got this written down. I believe I should be writing down, sorry, x2, that's a 2, sorry, minus, yeah, minus, and that's a 3. Sorry, x, yep, I did the wrong one here, so it's going to be that one. Okay, and let's put this one back to what it was, which is correct. Okay, so let me just check my notes. Minus 4x1. Yeah, x2 minus 3x1, and then x5 minus 2x1. Right, so x1, x2, x3, x4, and x5. All the other variables appear. So this is correct. So you can check your algebra. I've checked my algebra before. I just want to make sure I'm writing down properly. Okay, so it's a simultaneous system of equations. So I'm going to write them out now. So I have minus 4x1, and then I have minus 2x3. I'm going to look at them all together. So I need this to be 0 for consistency. Okay, so maybe I should just give myself a little bit of space here. Do that again. So for consistency, remember that was the question we posed at the top. When is the system consistent? Okay, so now we see the conditions. I'm going to write them here. I need minus 4x1. Okay, so I'm taking that first equation, minus 2x3 plus x4. Now, I'm not even going to write x6 down here. You could and put a 0 coefficient in front of all of it, but I don't need to because I know it's a parameter and I'll keep that in mind. So I'm going to put that right here. So x6, because I know my answer has 2 free parameters, as we'll see. I'm going to call it t3. Okay, so there's my x4. Now leave a space for x5, and I need that to be 0. Okay, so that came from the first equation, the first red dot. And then the second one is minus 3x1 plus x2, and I need that to be 0. And then the last equation was minus 2x1 plus x5 equal 0. So there we go. So there's our system of equations we need the xi's need to satisfy for x to be in that set. So that's our system, that's our homogeneous system that defines the subspace W. So I'll make a note here. This is the homogeneous system that defines, this is what we mean, the subspace. Okay, so we've done that, but let's continue on. I'm going to continue on and find a representation of the solution set for this system, and that will be another basis for this W. Okay, notice up here, this is not a basis because they're not linearly independent. Okay, in the row reduced form, there's not a leading one in front of each one of them. Sorry, up here. Sorry, am I doing that problem yet? I'm not doing that problem yet. Okay. If you did row reduce it, you wouldn't get 4 leading ones. Okay, so this is not quite the reduced row echelon form. It's a row echelon form. But you can see that 6 right here, I would make that a 1, and then I would have my 3 leading ones. So I'll just make a little note here. Maybe I'll use green. So coefficient matrix, and this is also tying into what we'll see just below. Matrix has 3 leading ones. So in our jargon down there, the rank is 3. So linearly dependent. Okay, dependent. All right. So the 4 vectors, v1, v2, v3, v4, are linearly dependent. So they're not a basis for the W. They span W. Remember, that's one condition of a basis. They span it, but they're not dependent. Or they're not independent. They're dependent. What I'm going to do down here is get a linearly independent set of vectors that span it. Okay, and this process of finding these vectors, as you'll see here, and it's not new to you, I'm just going to identify the parameters in these equations when I row reduce it, they automatically generates a linearly independent set of vectors. So let's do this. Let's solve this problem. So I'm going a bit further now than what the question asked. Okay, so we've already identified the homogeneous system. I'm going to go further and use that fact to get a basis for this W. Okay, so let's find what the xi's, what the solution set of this homogeneous system is. So here's the augmented matrix, minus 2, 0, 1, 0, minus 2, 0, 0, 1, 0, 0, 0, 0, 1, with the understanding that x6, which is not appearing here, although it is a variable in the problem, it's not in the equation, so it's a free variable already. Okay, so I'm not even, you could add a column here. I'll just do it in yellow. You could add a 0 column, 1, 2, 3, for the x6 variable. Okay, so I'm not saying there's no x6. It's just it doesn't appear in all these equations, and that can happen anytime. Someone gives you a system of equations. You can always ask, is there another variable that's just not appearing in this equation? Okay, typically it won't be because they would let you know, but here you have to keep that in mind. In fact, there is another variable there, okay, the one that's not appearing in those equations. It came from the original problem. So if you knew that, it just means that it appears in these equations with a 0 coefficient. So you could add a column of zeros. And if you think about it, that's not going to interfere with our row reduction or our consequence, except when we get to the very end to express our solution in terms of parameters, I'll have to remember that there is an x6, okay? If you forget that x6, you're going to be kind of stuck, right? Because you're going to go back and say, oh, my x vector, I found conditions on the xi's, but I only found a condition on the 5 of them. What about the 6th one, right? You'd be stuck there and you'd wonder what happened. Well, nothing happened. It's just that the x6 is a free variable in this problem. So I'm not going to put it in. And then we row reduce this. You can check yourself. It goes to 0, 0, 1. 0, 0, 1, okay, fine. And then what are the remaining terms? These are important. Minus 1/2. You know, we're in that stage now where we don't want to spend a lot of time doing tedious calculations. So if I were you, you have to be confident in your row reduction because you'll be asked to demonstrate that in assessments. But the purpose of this problem, right, was not to row reduce. It was to use row reduction to answer other questions. So I'm using software to do all the row reduction. You know that? I'm not going to risk making algebraic errors, and also I don't need to spend the time doing that. So I'm just using my software to row reduce the system once I've determined the system. Okay, so the issue is not the row reduction exercise for me and for you too in this problem, but you still need to know how to do the row reduction. Okay, so it's row reduced. All right, so let's read off the solution now. Okay, so there's 2 free variables. I'll call that variable, that's x4 and x5, okay? And then I have my t3 up there, okay? So now I'm going to read off my solution. So x1 is equal to 1/2 t2. X2 is equal to 3/2 t2. X3 is equal to this combination of t1 and t2. So 1/2 t1 minus t2, okay? And then my x4 I was designating to be t1, my x5 to be t2, and then my kind of mysterious variable x6 is t3. Fine. Now I'm going to show you how you extract a basis for the solution set. This is an expression of the solution set. Okay, so 3 parameters. I choose these 3 parameters freely, t1, t2, t3. Whatever the x's I get here, I'm guaranteed that that vector is in the span of those sets, which I call W. Okay, so that's fine. That's one way to describe it. But let's write this another way. So I'm going to write x vector. Okay, remember x vector is, maybe I should do it, 1, 2, 3, 4, 5, 6. Okay, so there's my x vector. I'm going to write it out as a linear combination of 3 vectors, 1 vector for each parameter. Okay, so there's my t1. All right, so now I go across the components of my x vector. I look at x1. What do I see in my in t1? I don't see anything there, so it doesn't depend on t1. Okay, what about x2? Does it depend on t1? It does not depend on t1. Does x3 depend on t1? It does. You see, there's a 1/2. x4 is t1, so there's a 1 and 0, 0. Okay, so there's one vector. And then t2, how does t2 appear in this equation? Well, there's a 1/2 up here. There's a 3/2. Okay, and then there's a -1. And then there's 0 and a 1 and a 0. And then there's my all-important t3, which doesn't appear anywhere except in the variable x6. All right, so I'm getting there. Let me call, I don't like fractions, okay? So here's what I'm going to do. Maybe I should say u1 tilde, u2 tilde for now, because I'm going to get rid of the tildes. All right, so i.e. x is a linear combination of the ui, i.e. x is in the span of these guys, which means that's W, okay? Okay, so any linear combination with u's is a vector, does create a vector that's in W, and conversely, any vector that's in W can be written as a particular linear combination of these u's, and they are linearly independent. As you can see, they're linearly independent because of all the zeros there. So, but here's what I'm going to write out. U1, now I'll go to row form. I'm just going to get rid of the fraction. So, and this is something you should keep in mind. Although the u tildes, as I've written them, is a basis, if I take a scalar multiple of these vectors, the new vectors will still be linearly independent, and the new vectors will still have the same span, so it's still a basis. So I'm going to take that freedom and multiply the first 2 vectors by 2, that's all, so that my u1 will be 2 times u1 tilde, right? So 0, 0, 1, 2, 0, 0. In other words, it's 2 u1 tilde. My u2 will be 2 times the u2 tilde, so 1, 3, minus 1, 0, 1, 2. Not quite that, right? So I'm multiplying it by 2. So 1, 3 minus 2, 0, 2, 0. And I'll take u3 just to be what it is. That's a 1 there. Good. So it's taking up a lot of room. So a basis for W, remember W originally was defined as a span of a set of vectors that didn't turn out to be a basis because they were not linearly independent, although they do span W because that's how W is defined, is now I have a basis for it. And this is an important calculation because we typically do want a basis for the subspaces we're talking about, not merely a set of vectors that span it. We want a basis. So what I've done here is I've extracted from that subspace through this method of identifying it with the solution set of a homogeneous system. I've extracted a set of linearly independent vectors. And this is the key step up here. Okay, what I'm doing here. I'm expressing this system of, this expression of the solutions in terms of the parameters as a linear combination of these three vectors, okay, one for each parameter. And they will always turn out to be linearly independent because of the way they're extracted from a row reduced matrix. Okay, they'll be guaranteed to be independent. Okay, so we did that problem. Now problem 3 is, we've done a fair bit of that. So use Gaussian elimination to determine linear independence. So I'm just going to point out C3. Okay, so we had W equals these vectors, V1, V4. Okay, so Gaussian elimination means form this array. So I should put in, and as you should do, so linear independence. Remember, you have to remember what that means. It's a certain vector equation. So I have to look at this equation. I have to look at a particular linear combination of these vectors. So it's similar to what I was doing above, except in this case, for the question of linear independence, the vector you're asking to write as a combination is the 0 vector. Okay, up there I had another vector. All right, so you get a system of equations. Okay, now because the right-hand side is the 0 vector, it's a homogeneous system, so I'll get this augmented matrix, and I'll just put down my vectors, V1, V1 to V4. So I won't write them all down. So there's my vector V1 as a column. There's my vector V2 as a column. There's my vector V3 as a column, and I've written it down above. I'll probably make mistakes if I try to write it again. And that's the coefficient matrix, right? For homogeneous systems, you don't need to write the augmented matrix. And then I row reduced it, okay? And I had 3 leading ones. So let me see if I can reproduce that. 0, I'll reproduce some form of it. Okay, 0, 1, minus 5, 0, 1, minus 5, sorry, 0, 1, minus 5, sorry, there's another 10 there, minus, sorry, yeah, there's only 4, right? So where'd that 5, that 5 is not there, by the way. Okay, yeah. So, and that means I can get rid of that term there. So when you row reduce it, it's going to look like that. And then you're going to have another 1 there, okay, which means I can eliminate this one by the row reduction. And then I have my 3 0 rows, which gave me those conditions, remember? So that's what its row reduced form is. And I see my 3 leading ones. Okay, so there's 3 leading ones. Okay, so the question now is, where is it here? Right. So the rank here is 3. Okay, 3 leading ones. Number of columns, number of vectors we started with, is 4. Okay. Now this means they're linearly dependent, and I'll explain why. Linearly dependent. Okay, but that was what the question was asked to do. Was what's the relationship between rank and linear dependence? Okay, well, if the rank is not the same as the number of columns, so in other words, the rank is not the same as the number of vectors you have, it's dependent, and that's because we have here, so there's a free variable. Remember, when the rank is less than the number of columns, it means one of those variables is a free variable. If there's a free variable, that means there's a parameter in your solution set. So there's many solutions. Okay. Okay. In particular, they're is a non-zero solution to this guy, right? It's not just the trivial solution. Okay, you have a free parameter. There's many solutions. There's many non-zero solutions. So it's linearly dependent. Okay, so that's how we can do that. That was 4. Good. Now this thing also tells us more about this set of vectors. So let me continue down here. We see that I can pick out what this linear combination is. Okay, so I see that my C1 is going to be minus 10t. My C2 will be 5t. My C3 is the free parameter, and C4 is 0. Okay, so there's the solution set. And then from this, we see that this combination, so I'll just factor out that t, minus 10 times V1 plus 5 V2 plus V3 equals 0. Okay, I just took the t out of them. And so this means that, can write one of these vectors as a linear combination of the other two. Okay, and I'll just give you one example of other two. Example. So for example, I can see that U3, or V, I'm calling them V's here, okay? Hopefully that's the same as I called them before. So V3 is equal to 10V1 minus 5V2, all right? And I should move this a little bit down further. Okay. That's my 5, my new 5. So remember, linear dependence, I mentioned it above, leads to the consequence that when a vector is in the span of that set that's linearly dependent, it can be written many ways as a linear combination. And this is the origin of it, is when they're dependent, there's a particular linear combination, and here there's many of them. I just took out one. I took t to be 1. There's a particular linear combination of some of the vectors that equals 0, not all 0 coefficients. And from that one equation, you can rewrite one of the vectors in terms of the others. So that what we conclude then is that the span, I can take away V3 from this, okay? So the span of V1, V2, V3, V4, which was what the W was defined as, I claim it's the same as the span of, let's just drop out, or V1, I guess I wanted to write. So I'm going to drop out my V1. Okay, so my V1 will be 1/2 V2, so that's another way to do it, minus 1/10 V3. So let's do it that way. That's the way I did it in my notes. So I just dropped my first vector. So it's going to be V2, V3, V4. Okay, because I can write V1 as a combination of the other vectors, if I take it out of the span, it doesn't affect it, right? Because, I'll just write this out for you. This is all useful stuff. If I take a vector that is a combination, okay, so it's in the span of these vectors, okay, I claim that I can write it as a span of the 3 vectors V2, V3, V4 simply by writing out where I see V1 here, I write 1/2 V2 minus 1/10 V3, okay? And then I continue on, A2, V2, A3, V3, A4, V4, and then I just rewrite that, group it all together so that I see something times U2, which would be the A2, and then I see what comes out of the V2 part here. It's A1 over 2, V2, okay? And then for the V3 part, I get an A3 from that line, but I get a piece of a V3 here. That's a minus A1 over 10 V3 plus A4 V4, okay? So this is telling me that it's a linear combination of these three vectors. So any vector that's a linear combination of those four is a linear combination of those three. So that's one direction of this equality of sets. And it's trivial to go the other way. If I take a vector from the span of these three, then of course it's in the span of these guys because I give the V1 coefficient there 0. All right. So that's the origin of this property that if you have a set of vectors that's not independent, so they're dependent, then their span means that any vector in their span can be written in many ways. If they're independent, there's only one way to do it. All right. So where are we now? Number 5. Right. So this is up here. Okay. So I think I've said enough about that, and you're probably getting tired, like I am. So now we can answer questions about dimension once we've done this work. Okay. Remember, dimension is the number of linearly independent vectors that span it. So what we've seen up here. So back to 4. Okay. So it's nice just to use one example. So see, in 4, we had this subspace W, which was the span of the 4 vectors. Now, if I give you a W like this, okay, so the dimension of W can't be bigger than the number of vectors there. Okay, so I know it's less than or equal to 4, because remember, a basis is a set of vectors that spans the subspace. So, and the dimension is the number of linearly independent vectors that span that subspace. All right, so I have a set of vectors that span it already. So that's an upper bound for the 4, or the dimension, but it could be smaller because these may not be independent. Okay, but the rank of this matrix, right, with these as columns, and remember why we were looking at this matrix. This was the matrix that we were studying to determine linear independence, is 3. Okay, so V1, V4 is not linearly independent. Sorry, I mean, not that, but, and we did extract the 3 vectors that do span it. Rank is 3, so the dimension of W is 3, okay? So it's actually less than 4. Okay, so to summarize, if you're given a subspace and you're asked for its dimension, you're obliged to address the problem of linear independence. And from that problem, when you find the reduced augmented matrix, or just the coefficient matrix from that problem, the rank of that matrix will tell you the dimension of the space, because the rank of the matrix is telling you how many linearly independent vectors there are there. Okay, so the rank equals the dimension. Finally, what do I want to do here? Finally, let's see now. Okay, so this one right here, let me just quickly do this. Find the basis and dimension, right? So this is a typical problem. Find the basis and the dimension. Well, these things go together. If you find a basis, you found the dimension. If you've determined the dimension, you've essentially found a basis also, because it will be in that reduced matrix. So here, this is what we have to do. So you're obliged to, the subspace they're talking about is the solution space of a system. Okay, so what I need is to determine the solution space or solution set, and I do that by row reduction. So I put my, I build my, in this case, because it's a homogeneous system, I just need the coefficient matrix. I row reduce, and you can see that, I mean, you do it. This can be row reduced to the what we call the identity matrix. So there's only, so the solution set, yeah, is only the trivial solution is this vector. So the dimension is 0. So that's our definition of even though you might think there's one vector there, we still call it 0, okay? Because it's not a line. A line is dimension 1. So let me do instead something from this problem. Let's just look at the first two equations, okay? So I've mentioned this before in one of my previous lectures. If you take two planes, remember this is a linear equation in 3 variables, so its solution set right here. Each one of these equations, its solution set is a plane in R3. So I'm just going to take 2 of them, not 3 of them. The fact that we did this here is that these 3 planes intersect at the point 0. Okay, so these are 3 planes that go through 0. I can see that here. Okay, if they didn't go through 0, they wouldn't even be a subspace. So they're through 0. So that's the only point they have in common. What I'm going to do now is just take 2 of them. So the first 2. Now, what we expect is a line, right? 2 planes typically intersect in a line. Well, let's see if we can find that here. Okay, so I'm going to row reduce. I'm going to do the same problem as I just finished. I'm going to find the solution set here. So there's my augmented matrix, and you row reduce this to 1, 0, 0, 1, minus 1, 1. Okay, so then I write out my solution set. So x1, this is my parameter. x3 is going to be my parameter. Okay, so I get x1 is t, x2 is minus t, and x3 is t. So I'm going to do that, what I did above there. So I'm going to write x as t times some vector, and I can see what it is. It's 1, minus 1, 1. Okay, so this is the solution set. Now, do you recognize that? X times t times some vector. It's a line. So this is a line. Okay, we recognize what a line is. All right, and this is what we expected. We expect 2 planes. Doesn't always have to happen, right? They could be parallel. 2 planes in R3 to intersect in a line. So this example illustrates answering that kind of question. What is the line of intersection between 2 planes in R3? Okay, this is how you do it. You row reduce those 2 equations in a line, and then you find a solution set, and then you express it this way, because I've identified, this is what we're calling D in the section on lines. I've identified the line by identifying this D. Point on the line is the origin, because it goes through the origin. And you can check that any point on line X, actually it should be written that way, you know, X bracket T, because it depends on T. So check that any point on the line is in both planes. So pick T's that you want, any T that you want, and you'll see that that values of x1, x2, x3 will satisfy both those 2 equations, okay, no matter what T you pick. Okay, we're finally done. So I'm done with the lecture here, and I will see you sometime later on, I'm not sure when.